Welcome everyone to this webinar. I have with me my two good friends who I've known for several years, and I'll tell you a little bit more about their background in a second. But this is going to be a great opportunity to hear from two people who have been thinking deeply about these topics for several years. I think Arun more on the user side, and Ira more on the builder and vendor side. So it'll be great to have two different perspectives. As you know, machine learning and AI are both hot topics in general, but more recently for enterprise. And one thing that enterprises share and have a lot of are temporal data and time series. So that's why I'm super excited to talk to these two gentlemen today, because time series and temporal data are usually great starting use cases for enterprise who are interested in getting serious about machine learning and AI. And so without further ado, I wanted to introduce our two main speakers today. So I'm more of in the background here. I am Ben Lorica. I am the Chief Data Scientist at Anomaly. I am also currently now chairing three big conferences, Strata Data, the Strata Data Conference, the O'Reilly Artificial Intelligence Conference, and TensorFlow World. So maybe I'll have you guys do a quick intro of yourselves. So basically, just at a high level, talk a little bit about your education and experience, and what led you to this particular set of topics around time series and anomaly detection in particular. So Arun, why don't we start with you?
Sure, thanks, Ben. So I finished my graduate studies back in 2008. It has been a long journey. So since my graduate school, I've been interested in performance analysis and diving more into the data. And anomaly detection is a topic which is an integral part of performance analysis, and anomalies surface in pretty much every domain, as we shall talk about later in the webinar. So over the course of my industry career, I've been working on anomaly detection in several places. Back at Twitter, along with my interns, we developed an open sourced anomaly detection system or technique which we use in an infrastructure context. And my team has been conducting extensive research and development on various fronts to address this challenge of anomaly detection. More recently, at Machine Zone, we were looking at fraud detection in the context of performance marketing. So fraud is just another manifestation of anomaly in the realm of marketing data. So you can have anomalies in impression data, click data, install data, or engagement data. So we built a lot of novel techniques to address anomaly detection. And I mean, I've known Ira and Ben for a long time, and we shall talk more about the general applicability of anomaly detection techniques as we move along in this webinar.
So Ira, very briefly.
Yeah, so thanks a lot, Ben and Arun, for having this panel. Yeah, so my background is in machine learning, but I actually started from signal processing, which is why I like time series data so much. I worked a lot on video, but then moved to time series analysis in my work at HP Labs and then HP Software. And 5 years ago, started a company around anomaly detection for time series data, which is what Anodot does.
All right, let's get started with the webinar itself, with a series of short presentations, and then followed by hopefully Q&A with all of you in the audience. So let's start by asking you all to raise your hand. So we have a couple of questions here for you, the audience. Is there a slide? Yeah, yep, here you go. So how many of you have attempted to build an anomaly detection system in your company or your organization? So raise your hand. So there's a feature that allows you to do so. So yeah, it'll be interesting to see actually.
Yeah, so I see there are 15 people who already raised their hands. 15, sorry, 17. That's pretty cool.
Pretty cool, yeah. Next, did what you do involve any of these things? Statistical or machine learning, or more specifically, deep learning? Or were you mostly using other techniques? I guess we should have probably narrowed this down to machine learning and deep learning, right? So,
Yeah. Oh, that's a huge part. So 11 out of the 17.
Very cool. So I guess the first question is, why care about anomaly detection at all, right? So, who should you be looking to in your business to drive an anomaly detection initiative? So Ira, you want to take a stab at answering these questions?
Sure, and of course I'm going to give it from the perspective of some of the work that we do with our customers and what we see them getting value out of. So really the type of anomaly detection we are looking at is on time series data. And what is a time series? It's a lot of different measurements that you have from your business. And there are, the measurements are, they start from the revenue and how many visitors you have on your site and how many people are buying on your e-commerce site. And it could be your telcos looking at how many calls are being made and how many calls are being dropped. And there are a lot of examples from industry. I think we can show. I have a slide here. So the type of incidents that you find using anomaly detection in an organization are cost a lot of money to organizations. So Gartner said that an incident costs on average $300,000 an hour if you're a large enterprise. 7% reduction in your latency already creates a big gap in revenue. 100 milliseconds basically creates 7% loss of revenue, or it takes 31 hours a week lost to incidents in organizations. So it costs a lot of money to have incidents, and anomaly detection has really been the new way using machine learning to find all these incidents as fast as possible before they cost so much. So that's really the type of things, and we have, there are plenty of examples I can give from our customers, but of course I can't share them. But there are a lot of them that you can see out there that are published, and if we go to the next slide, then I actually prepared a few examples. For example, just recently, Dutch emergency line was hit by a telco outage, which cost a lot of money and reputation, of course. App stores, applications going down. Target was hit by outages that cost them millions of dollars. So these type of failures, if they're not detected quickly, and fixed quickly, then they tend to cost quite a lot of money to any company. And anybody running a business, especially online businesses, know that this is very costly.
All right. So then it's good to kind of put in context why even care about anomaly detection, and to also kind of emphasize that anomaly detection applies to businesses that collect metrics, which is basically every business, and doesn't necessarily have to be confined to IT metrics, as Ira has emphasized. It could be business metrics. So now let's try to be more specific as to what it is that we're talking about here. So Arun, can you kind of help us kind of narrow down the scope of what is an anomaly detection system?
Sure. So, I mean, as Ben said, that anomaly detection need not be limited to IT metrics. It can also be business metrics. And let me give you a specific example. So back at Twitter, where we developed one of the early techniques, there were many business metrics or KPIs, such as number of tweets per second, or number of followers per second, or number of retweets per second. So these are business metrics, and if you see a sudden drop from what you typically expect, then that constitutes an anomaly. So at a high level, an anomaly corresponds to a deviation from an expected pattern. Of course, there are a lot of details which one needs to dive into. So we employed or we developed novel techniques to be able to detect any anomaly in a business metric or in our infra metrics for that matter. Why automated? So the key thing is that historically, people have been detecting these anomalies via dashboards. Now, if you attend conferences such as O'Reilly AI or O'Reilly Starter Data, it is pretty routine for speakers from leading companies such as Facebook, Netflix, Google, and so on and so forth, to share that in the interest of observability, they monitor hundreds of millions of time series. Now, at that scale, it's practically not viable to monitor and detect anomalies via dashboarding. So that necessitates organically to build automated anomaly detection, whereby you detect anomalies algorithmically and then marry that with the context and only surface those which warrant action.
Yeah. So if I can add maybe to what Arun said. So yeah, I've seen it also in my previous companies. The way people detect anomalies today, or basically detect unusual situation. What is an anomaly? An anomaly is something unexpected that happens, and in the context of a business, it's an incident or an opportunity that if you don't pay attention to it, it might cost you, or you have a missed opportunity. And the way, as Arun said, the way traditionally it's been done is either having people sitting down in front of dashboards all day long and actually looking for those unusual situations, but that doesn't scale. And when you have hundreds of millions, I think Facebook has billions of these time series collected all the time. So that's one way. And the other way is to try to create alerts and static alerts, basically saying if it crosses some threshold, then send me a notification, because I can't just look at everything. So that tends to work at either very small scale where you know your data really well, or if you have a very good understanding of what those thresholds should be. For example, if I'm monitoring a server, I know my CPU should not reach 100%. Let me find whenever it crosses 90%, or my disk space cannot be more than 95% full, otherwise it might reach its capacity. But when you're talking about a lot of application KPIs or time series, business metrics, it's really not clear what those thresholds are. There isn't really a good way to know. But people have done a lot of automatic thresholding using static thresholds. That tends to create a lot of false positives or missed detections. And it's also becomes a system that you have to maintain very, very constantly and very hard to do.
So how does anomaly detection IRA relate to machine learning?
So that's a great question. So basically, anomaly detection is a field in machine learning, right? It uses a lot of the algorithms for machine learning. It's an unsupervised machine learning area. And it's basically looking for the outliers. So the way I like to think of it, if in unsupervised learning you do clustering oftentimes, this is the extra step of saying, oh, something is not related to any common cluster that I can find in my data. And now the question is, how do you define a cluster? And that depends on the type of data that you have. If it's a time series, then you have to model it one way. If it's static data or non-time related data, then you use other techniques. But it's basically part of what we call unsupervised learning. I also think of it as something that that even in regular machine, in other parts of machine learning, you need to apply in order to get good training. For example, if I'm a machine learning practitioner and I want to I get a training set to do even a supervised task, I might want to discover my anomalies in the data so it doesn't bias or corrupt my my training data. But that's another area of anomaly detection.
Yeah. Actually, that's an area I'm super interested in around basically data quality, data cleaning, and these sorts of things. So Arun, so what are some of the common techniques that people should be looking towards implementing if they're, for example, getting started?
Yeah, so as Ira mentioned, that in most cases, one should explore using unsupervised techniques to build anomaly detection system, because in a real world scenario, it's very hard to get labels, and hence leveraging any supervised learning based techniques is not viable. Now, talking about in the unsupervised realm, there is a pretty extensive literature, but to get started, there are very simple techniques such as mean plus minus 3 sigma. So it's just as a starter, one can leverage rules like these. These are still far better than using a static threshold, because mean and standard deviation, they are function of the underlying distribution. Now, having said that, there are many underlying assumptions, which a simple rule like mean plus minus 3 sigma makes. So it's very important that even when one uses off-the-shelf rules or techniques like these, that the underlying assumptions are validated. So for instance, in this case, it assumes that the time series is stationary. It assumes that there is no seasonality, and it assumes a normal distribution. So these assumptions should be validated. Otherwise, you may end up with false positives or false negatives.
So actually, I wanted to add to what Arun said. So of course, there are a lot of unsupervised techniques, and one of the questions that Arun alluded to is why not use supervised techniques? When we talked about in the intro, how do they get to anomaly detection? When I started my work at HP, we faced a similar problem, but I wanted to solve it using supervised techniques, meaning I wanted to know, I know that if I do supervise and I have enough labels, the chances of me catching things and measuring how accurate I am is much better than unsupervised techniques, because the target is not very clear and you make a lot of assumptions on your data, as Arun said. The problem is that in a lot of the cases that we're talking about, there isn't a way to get labels of anomalies. And what I found when I tried to do this, and I tried to do it for a year, questioning people around IT, more the IT domain, questioning what are the common anomalies that happen in the world. Let me find those, label them, and train a supervised model, and maybe capture 80% of things. But I quickly found out that there aren't a good way to capture these labels from people, because all these systems that we're monitoring, all these applications, when they work okay, they all look alike. But when they start becoming faulty, or there are all sorts of things that go wrong, everything that goes wrong may look different than others. So it's very hard to actually even get the top 10 cases of things falling apart. So it's like Dostoevsky's book, you know, good families all look alike, but broken families are all different. And this is the same way with what we're dealing with, which is why we have to go to these unsupervised techniques and learn what is normal, because that is possible, and then find these abnormal patterns out of those.
Great. So we have a quick poll before we go to the next section. And so basically, we want to kind of take your temperature as to what is the most important component of an anomaly detection system. So give you folks a few seconds here to answer, and then we'll go on to the next section where we'll do a more detailed discussion as to requirements of what makes a successful anomaly detection system.
Oh, I see. There's at least one person who wants to find the anomalies in their significant other. Those are the most interesting things about the significant other. This is cool. Yeah, this is super interesting. It actually is in line with what we see.
All right. False positives, obviously, number one.
Real time, then real time.
Yep, real time now. That's becoming more and more important again, and it will become more important with 5G.
Oh yeah.
And then scale. Very cool. All right, so let's, because we're in a tight schedule here, let's jump into the next section, which is basically system requirements of a successful anomaly detection system. So here we'll just kind of have a free-flowing discussion, and Ira and Arun, feel free to jump in. But basically, what are some of the requirements that you think are critical for people? And I think we also should probably factor in that the audience here has many different entry points. Some probably are just getting started, and as we noted in the raise your hands earlier, some have already begun building anomaly detection systems. So requirements, Arun, you want to take a first stab?
Sure. So as the audience also highlighted, that real time and scale are pretty key to any anomaly detection system which one may want to use in a industry environment. As data availability becomes more and more ubiquitous, there'll be more and more data streams which will be flowing through the system. So to be able to extract anomalies in real time so that appropriate action can be taken, will hold key. So for instance, we had Amazon Prime Day yesterday and the day before. So imagine that if you are at Amazon Prime and then there are certain products which are selling like hotcakes, then Amazon would want to know these trending items so that they can revamp their inventory in time and minimize the lost sales. So surfacing these real-time insights is very important, and scale goes without saying that if you are a big enterprise, being able to scale because you are monitoring hundreds of millions of time series is also very critical.
So let me let me actually interject myself here quickly. So when we talk about real time, there's the notion of being able to process the data in real time, surface anomalies in real time. But Ira and I guess Arun as well, what about the ability to adapt and learn from a possible new changes in the state of the world? So real time or online learning.
Yeah, so I think that is actually critical, especially for this type of systems measuring businesses. If you're measuring system metrics or business metrics, the state of the world changes, and you have to have algorithms that are able to adapt quickly enough, detect the anomalies on one hand, but adapt to changes in the world fast enough to be able to catch new situations. It relates to the false positive, false negatives as well, because if you have, so the most important thing in the poll, the people shared are false positives, and I think this is really the perception that we also see. False positives is something critical to minimize, because like any system that you must act on, if it tells you something that is wrong and you waste time on it, then you lose your confidence and you start stopping using it. And that happens a lot in the old static threshold, because people get tons of alerts and get alert fatigue. So adapting to changes that are happening in the world is critical to reduce false positives and to still be able to catch the right things. And changes happen a lot in businesses. It's not like they're not closed systems that are designed once, built once, and are known to operate in the same way, like let's say an airplane engine or a big machine. It keeps changing, so it has to adapt. It has to use new data constantly to change what it knows about the world.
So Arun, are there different types of anomaly detection systems? So is there a simple taxonomy that people should keep in mind?
Sure. So as we had one of the earlier slides, broadly speaking, one can either employ techniques rooted in statistical learning or machine learning or deep learning. There is a vast amount of literature in all the three subdomains. And as I mentioned earlier, that anomalies manifest in different forms. You know, it can be from astronomy to manufacturing to operations or networking or what you have. So it has been studied for more than a century. Now, the taxonomy relates to the third bullet here we have on the slide, which is explainability. So the selection of the technique should be guided by your use case. You know, someone working in academia trying to or pursuing research in anomaly detection system is probably all right to just surface anomalies and show that the false positive rate is lower than state of the art and then move on. But for instances like what Anodot deals with, because they have real clients, you know, explainability is very important. So from my own personal experience back at Machine Zone, where we used to dispute fraud in our marketing campaigns. So fraud is, for the benefit of the audience, is one of the most rampant pain points in the realm of digital marketing. So whenever we used to surface fraud, it was imperative that we could explain why what we have surfaced is indeed fraudulent. So explainability to our ad partners was pivotal to get the money back. So, and that's where, you know, approaches like deep learning, which have shown a lot of promise in other domains such as speech synthesis or audio to text, text to audio conversion, and so on and so forth. In the realm of anomaly detection, when you're deploying it in an industry context, they tend to fall short, because there is lack of interpretability / explainability. There is, although there has been recent work or recent focus on improving the explainability of deep learning models, but they still have a way to go. So leveraging the taxonomy depending on the use case can be very helpful.
Yeah, I think that another aspect of that, besides explainability, is what the fifth bullet, I think, multivariate or univariate. So actually, when you go from, you can have a full multivariate technique where you have a model that learns normal based on the inputs from many, many different sensors. And then its output is, I found an anomaly in all these sensors or not. The problem with that approach, that if you need to explain why it said that there was an anomaly, it can be very, very challenging to do it. As opposed, for example, to univariate techniques that look at time series, each time series as its own variable and find anomalies in them. Those are easier to explain because you can show, oh, here, this time series value is now outside the norm, and I can draw the norm for you so you can see it and what I mean by normal. And that's really it relates to the explainability as well. And it kind of hampers the ability to use some multivariate techniques or more deeper techniques like deep learning in some cases, some use cases of anomaly detection. And there are other use cases, as Arun mentioned, that you can use the multivariate techniques because you don't necessarily need to explain the outcome. Maybe there is an automated action taking after an outcome that says there is an anomaly, and as long as it's mapped out correctly beforehand, you can take those actions. So it really depends on the use case. There is a lot of different techniques that you can use based on whether you need to explain it or not.
So what about, I recently been thinking a lot about the infrastructure ecosystem around machine learning itself, for which obviously a lot of that will feed into anomaly detection. So there people are starting to think about tools for model governance, model operations. So obviously in a system like Anodot, you can have many, many models out there in production. And so what sorts of best practices do you have in terms of introducing new models, retiring old models,
Right.
or basically QAing new models, right? So before you even introduce them to your system. So how do you know that these new techniques that Arun mentioned around deep learning are even worth the cost of deployment?
All right, so I can talk about some of the models we have, and maybe Arun can speak about some of his background around it. So definitely, when we have models that we want to deploy, there is of course the whole phase of developing it and testing it on some data that we put aside. But let's say we passed all of that, and there are a lot of best practices for that. If we pass all of that, then we still have to deploy these models into production, and then send them on their way and see what happens. The only way that we found to actually make sure that they still function in production is to monitor them directly as well, and actually use anomaly detection to find when they're starting to behave differently than before. I'll give you an example, not from Anodot. It's an example I really like to give for other types of machine learning algorithms. I think in December there was a glitch in the Google ad, one of their software for ads, that actually somebody introduced. There was some bug in their training software, and their bidding algorithm started bidding on many ads on the internet, and actually won a lot of them because it was really bidding way too high. And basically these bidding algorithms, they are usually based on machine learning techniques, and if something goes wrong with that model that is now doing actual bidding, it's going to overbid or create a lot of wrong bids in wrong places, and it's going to cost a lot of money. To Google, it actually cost, I read in the articles, anywhere from $1 million to $10 million in 1 hour of that glitch. And the way to catch it is to actually monitor what these models are doing and catching when they are starting to behave differently. And this is the anomaly detection. So what you see here on the slide is actually an example of a time series that you might measure. It could be revenue. And what you're seeing here on the screen is how do we learn what is normal about it? So we start out by very wide distribution in the beginning of the time series because we don't know what happens with it. Eventually we realize that there is some seasonal pattern to it, first daily, then weekly, and then we have a very good understanding of the normal behavior and we can detect anomalies. Now, when you're modeling, to your question, when you're tracking your machine learning models in production, they're actually going to produce a lot of these time series. Some may look like this one, some may look differently, may have different behaviors, non-stationary, stationary behaviors, but they are still going to exhibit some normal pattern. And that's the way we found is the best way to track them. And it's very similar to tracking your business. I mean, I think of machine learning models and their governance. Machine learning models in production, running in production, they're like, I think somebody from Gartner or Forrester called them AI workers. So they are just like any other part of the working environment of something constantly doing, taking actions and making decisions based on input data that it gets. So you have to monitor it just like you monitor the performance of any worker.
There's also the argument and the philosophy, I think, and in some regulated industries, even very strong guidelines around making how you organize your teams. In other words, you may have one team that develops the anomaly detection system and one completely independent team that just makes sure that it's correct, it's ready to go, and then monitors it. Arun, I wanted to actually very quickly get your take on, since you've mostly been on the side of someone who either builds or evaluates these systems. So any kind of high-level advice for our listeners as to how you would evaluate a system, an anomaly detection system, if you were on the side of someone who is deciding whether or not to use a specific anomaly detection system, what are some of the things you would look for?
Yeah, so the devil is always in the details. So if I were to evaluate an anomaly detection system, is to get some feel for what are the different models they support, and more importantly, that what are the underlying assumptions of the models make, and are those assumptions satisfied by the data at hand. So now, like a company like Anodot, who has invested a lot of time and effort in building such a system, so it's not particularly relevant or needed to dive into the technical details, but as long as the potential user of such a system, is, as long as, like, basically doing a due diligence that the product actually validates the assumptions of the models the model makes with the data. And if it is so, and the other thing is that one model doesn't fit all. So that's one of the nice things about a system like Anodot, that they have an ensemble of models. They don't rely on a single model, because the data characteristics are very different depending on the data source. So making sure that there is an ensemble of models, so that the final recommendation of the system will be much more robust than using one or two models.
So you're on the, so let's say, Arun, you're on the technical evaluation team, right? So now you kick the tires on the system. Now you have to convince some business decision makers. So how would you go about convincing them that a system is solid and good? And so it's just where kind of a system's ability to explain how results are being, decisions are being made becomes important. So what are some of the things that are critical to technical teams who want to convince their business decision makers?
So, so that's a great question. So yeah, if you roll back time, let's say I was still at Twitter, and then if we were evaluating a system to find anomalies in business metrics, then we would pilot the system, and we'll see that okay, how many times that whenever we had an incident or there was some other due to some other reason, our business metrics nosedived, or there was a sudden spike, maybe because of DDoS attack. How many times was the system under evaluation was able to detect, and what was the business value? So was it able to catch the key instances where our business could have been impacted materially? So that would make a very convincing business argument that look, for the smaller incidents, even it's not as material, but for the bigger ones, like if you're at Amazon and you expect sales of north of 100 million, but you see that hey, for the first 6 hours my sales are only 2 million, so it's a negative anomaly, and the system was able to catch it. So that would be a very convincing case that look, our business was getting impacted in a material fashion, and the system was able to catch it.
And obviously, I guess, Ira, there's certain operating requirements, right? So the ability to integrate, ability to ease of getting started. So how easy is it to feed data into a system? How soon before I get results, and things like that.
Yeah, I mean, so yeah, when we designed kind of the system, then we had to think about a lot of things from the algorithmic and product requirement. What is what does it actually have to have before it becomes really useful? So false positive, minimizing false positive, as the poll said, it's obvious. There was another part that 40% said it's important, which is scale. And the way I think about scale, and this is part of the requirements, both from the algorithm, but also from the product itself, the scalability is not just the ability to process a lot of data and process it fast in real time. But also to do this processing and analysis and finding of anomalies without any human intervention. Because if you're collecting millions of these time series and you want to find anomalies in all of them, if you start asking people questions, oh, what is this time series? Is this stationary or not? Is this seasonal, yes or no? Then you can't really scale with that. So it has to have, so scalability is both from the algorithm perspective, being really autonomous, learning everything that it can by itself as much as possible with minimum to zero human intervention. And then the product requirement around that is to have the ability to explain what the algorithms found. So finding an anomaly without explaining it and without having a product or having some way to explain why it was an anomaly, and usually the way to explain it is using some visualization. Show a graph with normal, how it looks normally, and then show that it's outside. It's very easy for us as humans to understand why it was an anomaly. So from the algorithm perspective, being very autonomous, being able to cope with a lot of different types of data distribution or seasonal patterns, adapting to varying situations. All of those are critical. And then from the product is being able to show the result in a way that the user, any user, can understand it, why it said so. And that's really a lot of the requirements we put ourselves, and scale is one of them. And scale actually the algorithms and the scale of them feeds into minimizing false positives. Scale feeds into being able to do it in real time. So that's part of the requirements. I don't know, maybe Arun, when you were working on the Twitter open source, or before it became an open source, did you get requirements from the business of what it should be?
No, the requirements is essentially what you just outlined, that in the infrastructure space, if we put ourselves in the shoes of a SRE, an SRE would not want to get a false positive pager at 3 a.m. If it happens even twice, the SRE is not going to use the system, going forward. So minimizing false positives is extremely important in that context. Now, the flip side is, let's say if you deploy the system in the healthcare space, then you would rather have false positives than false negatives, because if you have false negatives, you're putting someone's life at risk. So it is very context dependent. So yeah, back at Twitter, false positives was minimizing false positives was the key requirement, because otherwise you will have very low adoption. And then of course it has to be more real time, that if the system catches an anomaly which is indeed an anomaly and warrants action, but if you only surface it 2 hours later than the actual incident, then that would result in a very poor user experience. People are not able to tweet or retweet, and you don't want that incident to prolong for 2 hours. So timeliness is very important.
All right, so we have a few sections left. I want to go through these fast because I do want to get through some of the questions from the audience. So first, resources. So Arun, so what are the resources needed to support successful implementation in terms of people and budget? And are there any open source tools that are available?
So to get started, there are a lot of resources available out there currently in the realm of unsupervised learning. The default languages people use is either Python or R. So there are plenty of packages in both languages. And in fact, language is not a barrier. R is more popular in statistics, Python in CS, but you can use packages like RPy2 to call a R package from Python. So there are a lot of packages in both languages one can leverage to get started.
So, and then since people who are considering buying a system from a vendor or a cloud provider, it's also not just a question of budget, but processes as well, right? So you have to have a process for how to evaluate systems or even models from third parties.
Yeah, that's a good point. So this relates to what we discussed earlier, that to have integration support, that are there APIs which these vendors support, and as Ira mentioned, that being able to explain why an anomaly is an anomaly via dashboarding. So if someone has 10,000 time series, can the dashboard surface only relevant time series which are actionable, and then highlight why it is anomalous? That is very critical for evaluating the system. So someone which doesn't have a rich set of APIs or connectors to different data sources, be it Kafka, be it Hive, or Pulsar, that would be very limiting.
So Ira, I bet you get this question a lot, right? So, which is basically, your system is cool, but maybe we'll just build it ourselves. So
yeah, so that's it's always a valid question. So what we've seen, or what I've seen over the past 5 years, and even before that, so it's quite easy to get something going, something working on some of the data. Using a lot of these open sources. You still, in my opinion, need to have, if you want to seriously build a system that can handle, both scale and a wide variety of signals, you need to have data scientists that understand time series on board. It's not So they have to understand the unsupervised techniques and understand the special thing about time series as opposed to non-time series anomaly detection. So the time series means that you have to have models that take into account the temporal dynamics of different of what you're measuring. If you don't take into account temporal dynamics in some way within your algorithms, you're actually losing out and you're going to create a lot of false positives. And temporal dynamics is not easy to catch. Now, the way we've seen it, and we've seen a few examples of companies that a lot of them are our clients today, that started out as small startups. When they were in startup mode, they did not invest anything related to anomaly detection, maybe some basic alerting and dashboarding, but it's okay as long as you have, a lot of data. Your incident cost is probably a lot less than what you're making, and you don't have time or resources to invest in anything. So you're just handling it. And then we've seen that, after the first year and a half, you start getting a critical issue that costs you a lot. And, then the CEO and everybody starts getting nervous. But then it gets fixed and things move along until the next big one comes. Usually something that is overlooked, something it doesn't start as a major outage, but it starts as something much smaller and then, kind of slowly creates a big damage. And you lose a lot of money, and then everybody freaks, the board freaks, everybody freaks out, and now comes the moment that you decide to build something. And at that point, you have a decision. You can start building your own. You can buy from a vendor. If you decide to build, then you have to create a team around it with a data scientist or 2 or 3, depending on the size of the company. And how ambitious the plan is. Developers, you need backend, you need some testing, you need somebody to define the product if you're serious about it. And that takes time, it costs money. And at that time, you're spending money, but it's not solving your incident. So you still lose money and you hope you don't get another big one before you finish it. Unfortunately, a lot of times, people think of it as a project that starts and ends and not as a product that you have to keep and maintain, because you're building a internal product to do something, just like you would any other internal product. And if you don't continue to invest in it, when the project is done, you end up seeing that it doesn't work. And we've seen it happening a lot of times where it worked on some data, it worked in the lab, it worked in the development of the product, it works on a small subset of the data. But then if the investment doesn't continue constantly, it's not a project, it's a product. So you have to continue to invest.
And there's also, I think, there's also the question for data scientists, right? So, so in terms of, like you said, so first of all, it's a somewhat of a specialized topic, temporal dynamics and time series, but also data scientists might start questioning, should I be working on this, or should I be working on something that business people in my company really care about, right? So whatever the core business it is that we're involved in, be it finance or logistics, maybe I should be using my machine learning skills directly for the business. So let's jump to the next section. And here I want really brief answers because I do want to get to some of the questions. So 1 minute each. Of course, the big topic of this webinar is anomaly detection, but I think actually an equally massive topic for businesses these days is forecasting, and forecasting of all sorts, right? So nowadays, demand forecasting for retailers and logistics providers, everyone is thinking about forecasting. So will any of these topics or things that we talked about or systems that we've built, do any of these help me with forecasting? So 1 minute each. Arun.
Yeah, sure. So this is a very tightly coupled topic with anomaly detection. Any business, be it business metrics like your traffic volume or your sales, and if you're a public company, then you need to provide guidance to the Wall Street. And forecasting is very intimately tied to anomaly detection, because the data you're using, your forecast is as good as the model, but also the data. So if your data, historical data, has a lot of anomalies, your fidelity of your forecast will be pretty low. So it's very common that before you employ the state-of-the-art forecasting technique, whatever it may be, that you cleanse your data by leveraging anomaly detection techniques to ensure that the input to your forecasting algorithm is clean of anomalies. Otherwise, your forecast would not be as robust.
Ira, 1 minute.
Yeah, so basically, a lot of the techniques that find anomalies are also are forecasting techniques, because what are they doing? They're learning the normal pattern, and they're saying, okay, I expect the normal pattern in an hour or in a day or in a minute to be this. And then when the data arrives and it's not based on that forecast, that's an anomaly. That's the definition of that anomaly in that sense. So the techniques are tightly coupled, and the interesting part is what Arun said correctly, and I couldn't agree more, is that, you know, when you're trying to train forecasting models, the anomalies in your data can really hurt you. Can really hurt how you train your forecasting models, the accuracy of those forecasting models, and we've seen a lot of examples of that with lots of different types of data. All
right, so
you have to do something.
Before we jump to the Q&A, we do have one poll question. So if we can bring that up, which is basically, how important do you believe having anomaly detection is for your company, based on Ira's quick primer in the beginning and all the things we've talked about. So let's give you guys maybe 30 to 45 seconds to answer this, and then I'll go through some of the questions from the audience. All right.
So yeah, this is interesting. So I thought maybe, you know, it would have been nice if we gave only critical, super critical, and really, really critical.
All right. So now to audience questions. So I'm going to skip around because some of these we may have addressed more during the presentation, but I'll try to get to as many of these as possible. We only have a couple of minutes left here. So first of all, to both of you, what is a reasonable false positive rate? I guess it really depends, right? So, but yeah. So Arun.
So yeah.
So can you repeat the question?
What is a reasonable false positive rate?
Yeah, so again, it depends on the context, but let's say if you are in the ops team, and if you get more than 5% false positive rate, and it also depends whether it's
what time of day you're getting.
Yeah, exactly. So now, without putting too many if that, yeah, I think anything more than 5% would probably have a low adoption rate. I mean, and I'm being very conservative here. Yeah.
So actually,
yeah.
let's move forward, Ira, so that we can answer more questions. So I'll have one of you answer each of these questions. So Ira, so which criteria can we use to determine which anomaly detection method is more likely to be suitable in each case?
So that's that's a great question. The best way is to actually have some known anomalies in the data and run multiple methods and see which one produces the lowest false positive rate and catches the true ones with the highest. So do any type of ROC analysis or any other type of analysis. If there is no label data at all, then really you're left with some measures that are proxies of the quality. And what we found to work best is to first look at how well do we forecast, does the algorithm forecast the next samples on one hand, and then on the other hand, how many anomalies does it produce? And you want to do a trade-off between the two, because it can get a very accurate and narrow forecast, but it might produce a lot of anomalies, and most likely a lot of them are not correct. So there is a trade-off between those two, and that would be, if you have no labels, that would be the selection criteria.
So Arun, very briefly, what are some of the pros and cons of open source code, using open source projects for something mission critical like this?
Yeah, so I can speak from my own experience. You know, what we built at Twitter, we never claimed that it will work in every context. So it's very important to understand that people have this tendency to use things off the shelf and expect it to work, especially in the realm of anomaly detection. Anomalies are very contextual in nature. So it's very unlikely that something you grab from the internet, unless it was built for the same domain, will work out of the box. So you will either have to tune the models or you may have to develop new models. So keep that in mind, you know, as you're exploring the use of models out there in open source.
And also, as Ira alluded to earlier, it's one thing to build an anomaly detection system for one-time series,
Yeah.
but to really do it systematically at scale, somewhat semi-autonomously with lower operating costs is another matter. So Ira, question from the audience, which is, do you have any suggestions as to how people can reduce false positives? That's a kind of a
wow, that's a long, it can be a very, very long answer. So the best way we found to do it is to actually get feedbacks on alerts on anomalies that we find for different, I mean, if you're building it for some group, collect their feedback when they get the alert itself. And then when you collect it, so Debbie, if you can mute your line. So when you collect it, then you can actually go back and fix what's wrong with it. That's the only way we found to really reduce false positives, especially because of context. A lot of time there is context around what is an anomaly, and even if mathematically it looks like a huge anomaly, from a contextual point of view, your users might not view it as an anomaly at all, or might not view it as an actionable anomaly that they want to get. So you have to collect that feedback, and that's the way we build it to really fixing. It still has to work with minimizing false positive out of the box as much as possible, but if you want to get the extra mile and to get to that 5% that Arun was alluding to, that's the way to go. Without it, we've seen it go around 20%, 15% false positive, 10%, and it's still much better than a lot of the static threshold methods out there, much lower. And it also depends on the quantity. So if you send 100 alerts with 20% false positives, it's not the same as sending 10 alerts with 20% false positives a day. So it depends on that as well.
So this might be a question back to you, Ira, but Arun, feel free to weigh in. But very briefly, how do you tackle the curse of dimensionality when you are using unsupervised anomaly detection in a multivariate time series?
Oh, yeah, that's a tough one. So a lot of regularization. So you have to have regularizers in every type of model that you're using. For example, in some of the models that we're using, even the univariate ones, we have either Bayesian priors that regularize the output of the models. And if you have other types of models you want to regularize, if you're using LSTM, you want to do dropout. So each model has its own technique, but it must be there. Otherwise, it overfits like crazy.
So I think that's all the time we have. I'd like to thank Ira and Arun once again. And on a personal note, both Ira and Arun give the most popular talk at our AI conference. They usually give a joint presentation on deep learning for time series. So it's great to do this with you too. And it's funny because I think I'm the one who brought you guys together to begin with.
Yes, you did. That's right. That's right.
Forced marriage, but yeah. So this has been great, and our coordinator Debbie has her email up. So if you have further questions, feel free to ping Debbie. But other than that, thank you all for joining us today.